Is it okay? Okay. So let's get started. I mean, it's been 2 weeks that we haven't had regular class. Okay, 1 week for the winter break, not winter break. I mean spring break, for the spring break, and 1 week for the midterm. Talking about midterm, how do you guys feel about the difficulty level of the midterm? Is it difficult, or is it okay, or is it easy?
Harder than okay.
How do you mean?
Harder than okay.
Is it easy or is it hard? No input? Okay. If you check out the midterm, the question in the midterm, you will see that a lot of questions actually comes from the part of the homework. Okay. And if you have done your homework, you should have no problem getting a good grade. Okay. I mean, I don't think that's unreasonable like a request for you guys to work on the homework, right? Okay. So other than that, of course, I also have some other questions in the, other than the homework, but those other questions should be pretty easy to handle. Okay. So if you have problem with the difficult level of the midterm, you may want to work harder. Otherwise, I'm afraid you will not get a good grade. Okay, and I will have the TA return the midterm grade to you guys before the next lecture. Okay, so you can know your status, okay, in this class. Okay. So back to the lecture. Okay. So today we are going to talk about the Dirichlet triangulation. Okay. The Dirichlet triangulation, if you guys remember, I mentioned about 3 problems I considered like the most important in computational geometry. Okay, one is convex hull. One is the second one is the Voronoi diagram. The third one is the Dirichlet triangulation. Okay, I do not expect we'll be able to finish this chapter today. Okay, I estimate that we should be probably one proof less than what I can cover today. Okay, but anyway, let's see what I can do. Okay, so just like every other topic in this class, okay, we will start by a motivated problem. Okay, the height interpolation. Okay, so we know, like when you have a map, the map will tell you, okay, roughly like the height of each location, right? But how does the map store that height location? Obviously, it cannot like obtain the location for every point on the surface. That's just not possible, right? So normally we do it through sampling. Okay, This is like if you have ever climbed a mountain, okay, you will see like some kind of like survey point, okay. In Chinese, we call it 三角点. Do you know that? Nobody? Okay. Basically, it's kind of like a small piece of stone, okay, and it should be very obvious, like it is like used for survey purpose, okay, and that's basically the sample point, okay, which is used to estimate the height of your of the terrain, okay. So basically, okay, when you have this sample point, okay, you obviously, I mean, you don't want to say, okay, then the area close to this point, okay, will be this height, and area close to this point will be this height. Normally, you don't do that. Instead, what you are going to do is that, okay, you are going to, for example, in between these 2 points, okay, the height in between these 2 points will be computed by interpolations, right? This is very easy, right? Okay, so that place is like 100 meters. This place is 0 meter. Some, in between, okay, at the middle, the height should be 50, right? So it's a very easy way for us to estimate the height, right? But now we are not talking about just the line segments, okay? We are talking about surface. So, okay, what will actually happen is something like this. We are going to, triangulate this sample point. And then, okay, for each triangle, okay, we have the height for the 3 vertices, the exact height of the 3 vertices. And we can use that to estimate like the height of, well, any point in that triangle, right? By using interpolation. Okay, so this is like how the the height of the terrain stored in a GIS, in a geographical information system. Okay, so this is like otherwise, I mean, as I said, you just couldn't do like store the height for every point. That's just not possible, right? But there's one issue here. For a given set of points, okay, remember, we talked about like a triangulation earlier, right? We talked about triangulation earlier. Remember the art gallery problem, okay? Remember the Y monotone pieces. Okay, so this is not a new problem, right? However, you know, like there are multiple ways to triangulate a set of points, right? I mean, in the art gallery chapter, our purpose was just to find one way to triangulate those points, right? We didn't really care that much about the quality of the triangulation, right? We didn't discuss about the quality of the triangulation, right? So now, okay, let's look at these 2 figures. Okay, I mean, these two figures are the triangulation for the same set of points. And obviously, I mean, because we are focusing on the representing the height of the terrain. So the points, okay, the points will, each point, sample point will be associated with the height. Okay, so from here, okay, you can see that, okay, if you look closer at the height of this sample point, I think it should be very easy for you to realize that in the middle, there are some mountains in the middle, right? Right? Because on the left-hand side, the height is very low. On the right-hand side, well, it's higher than the left-hand side, but still like quite. I mean, the height is still very low. Okay, but in the middle, you can see it's 1,200, it's like 1,980, 990, like 1,890. So in the middle, you can see obviously this is a mountain, basically, right? So think about this. Okay. So this is one triangulation. This is another triangulation. Okay. But if you use this triangulation, okay, let's see when you use interpolation to obtain the height of this particular point Q, what happens? Okay. Because for this point Q, you can obviously see that, okay, on the two sides of this line segment, one end is 980, the other end is 990, right? So if you use interpolation, the height of Q obviously will be 985, right? Right? Okay. And, you know, by using this triangulation, however, by using this triangulation, okay, the Q is also in the middle of this line segment, okay, and the left side, okay, the height is 10, the right side height is 36. So if you use these two ends to do the interpolation, okay, for the height of Q, it's going to be 23. So let me ask you this question. Which one look more likely, look more plausible? The left-hand side or right-hand side? You do the judge. Huh? Left-hand side. Anybody else? How many of you think left-hand side is better? 1, 2, 3, 4. Okay. Okay, 5. Okay. How many of you think the right-hand side is better? Nobody?
I think we can decide the answer based on just these two, because maybe the right-hand side is just the same.
I haven't finished. Don't jump into the conclusion. I didn't say which one is better. Okay? I didn't say that, right? So don't jump into conclusion. Okay, I'm just asking you guys your opinions. Don't worry, okay? Don't be so judgmental so quickly, okay? Okay. So, yes, okay. If you agree with the left-hand side, in some sense, you think this line kind of represent ridge line. Do you know ridge line? 中文怎么讲？零线 yeah, 零线 Okay, just when you climb a mountain, you know, so when you go from one mountain to the other, normally the path you go is ridge line. By going through the ridge line, you stay at about the same height, and it help you to travel through the mountainous area. Okay, and so if you agree on this triangulation, so this represent the ridge line. Okay, if you agree that, well, it happened we have a valley, we have a canyon in between these two mountains. There's a very steep canyon in between these two mountains. Yeah, that's also possible, right? So look, I didn't say the right-hand side is bad, okay? Because, we don't know which area we are talking about, right? So don't be so judgmental, okay? So, however, I mean, if you study the geography, I mean, for long enough, you will understand that, okay, for a canyon to appear in between, for a very deep canyon to appear in between two high mountains, the chance is very low, right? The chance is very low. I'm not saying it's not possible, but the chance is low, especially when they are so close. When these 2 points, these two mountains, top of mountains are so close, and you happen to have a very steep drop in between, okay? It's not impossible, but it's unlikely, okay? So on the other hand, okay, this ridge line, I mean, is very common in mountain area, okay? So this brings an interesting question, okay? It looks like the triangulation of the left-hand side is better than the triangulation of the right-hand side, okay? Because obviously, okay, when you do the interpolation, it tends to be consistent with your intuition. Okay, even though we only have 5 students agree on the left-hand side, okay, but nobody agree on the right-hand side anyway. Okay, so I will assume the left-hand side is more intuitive. Okay. But how do we define these things? How do we define these things? I mean, how do we say one triangulation is better than the other? Okay. So there are a couple of notations to introduce. Oh, by the way, the slide, okay, that I'm using, you will see that it's slightly different than the handout that I gave you in EE class. It's because for some reason the new PowerPoint version doesn't handle the old PowerPoint file very well. So somehow some part of the slide will not be able to be visible. It will not be visible, okay, to you guys. So if I have to recreate some pages in order for my content to be visible, okay? So most of the contents are basically the same, okay? If you are worried about slightly different content, I will have the TA post this new handout, okay, to you guys, okay. So, okay, so let's first define what we call maximal planar subdivision. Okay, what is a maximal planar subdivision? Okay, it is a subdivision S, okay, such that no edge connecting two vertices can be added to S without destroying its planarity. Okay, so so if you add one more edge, that edge is going to, what should I say, like intersect with another edge. That is what we mean by destroying the planarity. Okay. So obviously, okay, this is perhaps another way to call a triangulation. Okay, because once you triangulate a set of points, well, you will, I mean, it is going to be a maximal planar subdivision, right? Okay, so do I need to prove that? I think this is obvious, right? Okay, so let P, okay, the point set P, okay, with n points, be a set of points in the plane. The triangulation of P is now defined as a maximal planar subdivision whose vertex set is P. Okay, so as I said, this should be obvious to you guys. Okay, and then, okay, when we look closer into this triangulation, okay, one thing interesting comes up. Okay, remember I told you guys like actually convex hull has something to do, it has some connection to the Voronoi diagram, right? Not exactly the regular Voronoi diagram, but at least like the furthest point Voronoi diagram, right? Remember? Okay, only the vertex in the convex hull will have a cell in the furthest point Voronoi diagram. Remember? I mean, you guys just took the midterm, right? Okay, so this should be, so there are a lot of connections between these three, as I say, like important computational geometry question. So here, okay, you can see, okay, the boundary, the union of these triangulations, its boundary will form a convex hull. Okay, so this again should be obvious, right? Should be very obvious to you, right? When you draw it, okay, I mean the outside of all these points, okay, is the convex hull, which happens to be the union of all those these triangulations, right? So now, okay, let P be a set of n points in a plane, okay, not all collinear. Okay, if they are all collinear, then it is like how should I say, like you cannot draw a triangle out of that, right? I mean, in order to draw a triangle, these 3 points cannot be on the same line, right? Okay, so you have to make sure these n points are not all collinear. You don't have to have like to guarantee like every 3 points are not on the same line. You just need to make sure at least one point is not on the same line as the other points. Okay, so and that K denote the number of points in P that lies on the boundary of the convex hull. Okay, so the n is number of points. K is number of vertices in your convex hull. Okay, when I say vertex, I mean I'm abusing the notation a little bit here, okay? Because you can see that, okay, here, okay, this is one straight line, right? It is one straight line. But if you use the regular convex hull definition, there are only two vertices on the two ends of this this line segment. But in this chapter, okay, when we talk about this, I mean this side of convex hull, they are actually 1, 2, 3, 4. We actually have 4 points. They are collinear, and they happen to be one side of convex hull. We will count them all. Okay, I mean we will count them all in this K. Okay. So, okay. Any triangulation of P, okay, here, I mean, it doesn't matter what triangulation we use, okay, any triangulation has 2n minus 2 minus k triangles and 3n minus 3 minus k edges. Okay. Obviously, k is bounded by n, right? So you can see that the number of triangles and number of edges are linear to the number of points. Right? Okay, so this is how do we obtain that? Okay, again, Euler formula come in very handy here. Okay, so we know like number of vertices minus number of edges plus number of faces will be 2. Right? This is known from the Euler formula. And the number of vertices, I mean, in this case, obviously is n, right? Okay, each node will be a vertex. I mean, for this this graph anyway. And then number of faces. Okay, how many faces do we have? Okay, let's assume we have totally n. Totally, we have n triangles. Okay? Each triangle is a face, right? And we have one additional face outside, right? So nf is going to be n plus 1, right? How about the number of edges? Okay, here, okay, we know each triangle has 3 edges, right? Each triangle has 3 edges. So when you count, I mean, all the edges from all the triangles, it's going to be 3n, right? But be careful, okay? When you do this calculation, I mean, for example, this edge will be counted for this triangle and this triangle too, right? A lot of edges will be used for the triangle on both on what I mean 2 sides. So that edge will be actually will be counted twice, right? Okay. What are the edges that will not only be counted once? These are the edges like that appear in the convex hull, because only this triangle will count this edge once, right? Okay, so now, okay, we want every edge to be counted twice so that we add them up and divide it by 2 to get the number of edge. So in order to do that, okay, remember, I mean, because only this boundary will be counted once, right? So now we add a k so that all the edges will be counted twice. Okay, so 3n plus k means like all edges will be counted twice. And then we divide this result by 2 to get the number of edges. Okay, so we plug in n plus 1 in this formula, and as well as 3n plus k divided by 2 in this formula. Okay, then it's going to, we are going to be able to represent, because we will only have like n and m, right? We will only have n and m. After you plug in the nf and ne, right? And you can easily obtain the relationship between n and m, right? And once you have that, once you can represent m by the combination of n, you plug in that into here, you will get the number of faces and the number of edges. Okay, and the number of faces minus 1 will be number of triangles. Okay, obviously. Okay, so do I need to calculate that for you? I think you guys can do that yourself, right? Okay, should be easy enough. Okay, this is at most high school math, right? Okay, so then we need to define a very important concept, and this concept is very interesting as well. Okay, we call that angle vector. Okay, after we triangulate those n points, remember we will end up having m triangles, right? We will end up having m triangles, right? So each triangle will give us 3 angles, right? Let me repeat. The triangulation will result in m triangles, okay? And each triangle will give us 3 angles, right? So total will be, we will have 3m angles, right? The total, for total, we will have 3m angles, okay? We can list all those angles, okay, in an increasing order, okay, and we say they are alpha 1, alpha 2, blah, 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 to alpha 3m, okay, because we have 3m number of angles, okay, and obviously, as I said, because it is in increasing order, okay, so the alpha I will be smaller or equal to alpha j as long as I smaller than j, right? Okay, so we call this, okay, this alpha 1, alpha 2, blah, 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 to alpha 3m. We call this as AT, okay, as the angle vector for the triangulation T. Okay, angle vector of T. So far so good, right? Okay. And then remember I told you, okay, there are many different ways to triangulate a set of points, right? So now, okay, we actually will be using the angle vector to evaluate the quality of the triangulation. Okay, so how do we evaluate? Okay, I mean, we need to define large, small, this comparison relationship between different angle vector. Okay, so for, say you have 2 different triangulations. One is T, one is T prime. Okay? Each one will give you an angle vector, right? Each one will give you an angle vector, obviously, right? So, okay, we say, okay, the angle vector t is larger than the angle vector of t prime. Okay, if at is lexicographically larger than at prime. Okay, so you may have question, what do we mean by lexicographically larger? Okay, basically it means that, okay, there exists an index I, okay, this index I, okay, is obviously it is in between 1 and 3m, okay, such that, okay, before index I, I mean these two angle vector, I mean each of the angles will be the same. The alpha 1 will be the same as alpha 1 prime. Alpha 2 will be the same as alpha 2 prime, and so on. Okay? Remember, it's in increasing order, okay? Both angle vectors those angles are in increasing order. So the before the index I, okay, the component in angle vector are basically the same. But for index I, alpha I is greater than alpha I prime. If that's the case, it means that you can, you put two angle vectors side by side, okay? Or you can see, these two are the same, these two are the same, these two are the same. Or you find the first pair that are different. Whichever is larger, that angle vector is larger. Okay? So that's the basic idea, how you compare the angle vector. Okay? How you compare the angle vector. So far so good, right? You guys are still with me. Okay. So we said a triangulation T is angle optimal. Okay, this is what we are looking for. Angle optimal. If AT, the angle vector of T, is greater or equal to angle vector of AT prime for all triangulations. Okay, so AT, if the triangulation, its angle vector is, you can say it's a max, it's the largest among all the triangulations, then we say this triangulation is angle optimal. Okay, so this is the way we use to evaluate the quality of triangulation. Okay, so far I haven't used a single word of Delaunay triangulations, right? I haven't talked about that yet. Okay, but I will. Pretty soon. Okay, but before we talk about more content, okay, there's some junior high school mathematics that we need to review, okay, which is called Thales theorem. In Chinese, it's called 泰勒斯定理. I don't know if you guys, this is very easy, okay? Basically, like, for a circle, okay, for any straight line that intersect with the circle at point A and B, okay, so it just, this Thales theorem just say, okay, if your point, okay, R is inside the circle, and of course, and S is outside of circle, and PQ are at the circumferences of the circle, okay, and these 4 points are on one side of this straight line AB, okay, on the same side of this line AB. Then we know, okay, the degree of ASB is going to be smaller than the degree of APB, which will be the same as the degree of AQB, and which again will be smaller than the degree of ARB. Do I need to prove that? This is junior high school math. Okay. If you okay. First, about okay. If you have any this is AB, right? Let's first prove this is P, right? We have another Q. Actually, it's probably easier if we just prove that, okay, the angle APB, okay, APB is, half of the, if this is the center is O, say the center is O. Okay, this angle is half of this angle, right? You should know that from junior high, right? How to prove that?
For the line PO.
Huh?
For the line segment PO.
Uh-huh. Good.
刚刚的 English term， 那个外角等于内对角的直角。
Okay, here, okay. Let me use another pen. This pen is it's not good. Do we have? Okay. So okay, so you can see this part, this angle, okay, is the sum of these two angles, right? Right? Because, okay, when we draw a line PO, okay, and extend it past this point O, okay, then this delta is like the sum of these two small delta, right? And this big cross is the sum of these two small cross, right? Right? So this whole angle, I mean, the reason I say it's a too small angle is because, okay, this line and this line, okay, are the same, right? The lengths are the same, right? So for this triangle, okay, these two angles are the same, right? Okay, 等腰三角形. Okay, for similar reason, okay, this, if you look at this triangle, okay, the lengths here and the lengths there are the same. I mean, they are all, the radius are, right? So this small cross and this small cross, they should be the same, right? Okay, so we know this big angle is the sum of big delta plus big cross, right? This big delta plus big cross is equal to 2 small delta plus 2 small cross, right? And this one is 1 small delta plus 1 small cross, right? So that's why this angle is twice of this angle, right? So this is junior high, okay. So we just review, 这个叫什么？这个叫圆周角是2倍的是圆心角的1/2 ，right? Okay, we I mean, but I forgot 圆周角圆心角的 English. Okay, I forgot the English of these terms. But anyway, okay, so first thing we know APB and AQB. I mean, these two are I mean, basically, I mean, facing the same arc, right? Okay, so they'll be half of the same, you know, AOB. They'll be half of the AOB. Okay, both will be half of the AOB. So APB and AQB, they have the same degree, right? Okay, so we have that, right? So how about this part and this part? Okay, well, let's take a 10 minutes break. When we come back, let's continue, okay?